Okay, example time of the trig substitution, the mother of all integration techniques. Now, as I mentioned in the lesson video, the goal to these is to use the trig identities, replace them with what they're equivalent to, and then simplify it so that the radical goes away, all the x's go away, and you're left with trig functions, and you'll be left with a trig integral. So the very first one, right? Our goal was to look for things like this. 1 minus sine squared, tan squared plus 1, or secant squared minus 1. This one does not look like the first one. It kind of does, but it's reversed, right? The x squared would be there. If this had been 4 minus x squared, you would pick x to be sine. But in this case, so it's not that one, and it's not that one. So in this case, I'm going to pick x to be secant theta. Now, as I said in the lesson video, and if you didn't watch it, it's fine. Since you are changing variables, right? The whole point of changing variables is to change the variable. So you cannot just say x equals sine x. That makes absolutely no fucking sense whatsoever. So they use theta. This is just what they do. They don't pick y. They don't pick alpha, beta. I mean, you can pick these things, but they pick theta, okay? So my line went a little off there. So now notice that I didn't write this question this way. And I don't put it this way when I put them on the sheets or on the test. People mess this part up. So, right? It's what it really is 1 over that dx. But for your convenience, and believe me, it is for your convenience, I'm putting the dx upstairs because that's where it's supposed to go. A dx here would mean that it goes on the top of the fraction. So I'm going to take the derivative of secant theta, which is secant theta tan theta d theta. Please use the correct notation. Do not put x's here. So if the x is there, it's going to get marked. It just shows me that you don't understand. You're going to get marked points off. Not marked totally wrong. So it depends on what you do next, right? Now, I have to point out something but this is the setup. But there's one thing that I'm going to show you, and it's not going to work. I want to replace x with secant, right? So you would put secant there. Now, that would give me secant squared minus 4. Now, you might think, oh, just take square root of that, square root of that. It doesn't work that way, right? You can't do that. So I really need a 4 here, and I don't have one there. So it messes up the question. This is the step that I'm always going to do on the side. So I have to go back and adjust my question. Whatever number's there, it's going to be a 4. It's going to be a 9. It's going to be a 16. If it's a 1, you're set. If it's a 1, you just do that. So, but whatever it is, whatever number is there, it has to be a perfect square. You're like, what if it's a 3? It's not going to be a 3. So I have to take the square root of 4 and I have to put it there. Okay, now in a minute, well, I'm going to do this first. Let me start replacing everything there. So dx, which I put on the top of the fraction, is equal to that, right? That's the derivative. Now I got to put a 2 there to adjust for that, right? I have a 2 there, so the derivative is 2. So a lot of times these 2's are going to kind of eat each other up when you do the problem. You'll see. So I'm going to put the dx upstairs where it belongs. It's 2 secant theta tan theta d theta, right? So you replace the top with what it's equal to, right? Dx is equal to that. That's the derivative of the x. That was my x. Took its derivative, put that on top. Now, x squared, right? You got to replace x with 2 secant theta, and you got to do the same thing inside the radical. Where the x was, right? That's where x was. X was here. Instead of x, you're going to put 2 secant theta. These are very, very nasty. You got to really keep track of your shit here. Now I'm going to stop a minute. Remember, my d theta is here, so I don't. If you really wanted to, you can put the d theta here. This is leave it where it is. Now, this work I am going to do over here on the side. If you want to ignore my advice, then you're a fool, and you'll end up writing this thing 6 times. I'm going to take this and put it on the side, and I'm going to bang it out and see what it's equal to. I know that if I square that, I times it by itself. So I have to do 2 times 2, which is 4. Secant times secant, which is secant squared. Theta minus 4. That's the identity that I want. Okay? Now, there's a 4 here. There's a 4 here. If I ask you to factor 4x squared minus 4, the first thing you would do is factor out a 4. You have to factor out the GCF, so that's what I'm going to do. I'm going to take 4, and I'm going to factor it out from there. I'm going to take the 4 from here. That leaves me with secant squared. I'm going to take the 4 from there. That leaves me with a 1. See? First step. Square that, pow. Factor out the 4, pow. Now, you replace that with the identity, right? Those Pythagorean identities with all the squares. This is tan squared. This was the whole fucking point of doing this, because now my very next step is going to be, this is a product. You are allowed to do the square root with a product. You are not allowed to do it with a sum or difference. So the 4 comes out of the radical, and then square root of tan squared is tan. So this crazy thing right here, on the side, you do all this work. That whole thing just becomes 2 tan. So now I'm going to rewrite my integral. I am going to square this, by the way. So on the top, I have 2 secant theta, tan theta, right? D theta. That's the top of my fraction. This is the reason why you don't do all this shit over here, because then you would just be writing all of this again and again and again. You take the radical part, you write it on the side, and you simplify it, and then you replace it. So this, right, 2 times 2, just like I did inside the radical, that's secant squared. And then this whole thing became 2 tan. Now this is what I was telling you was going to happen. I replaced everything that had x's with trig functions, and in this case, tans and secants. So cross out, boop, look, tan and tan, cross out. That 2 and that 2, cross out. And put little ones there so you keep track of who got crossed out. I'm going to cross out, right? You have secant squared. So there's 1 up there, and there's 2 down there. So one of those goes away, right? That 4 is still there, nothing crossed it out. Look at everything that went away. Gone, gone, gone. So my integral, which, as you can see, I'm not going to have room here. On top, I got a 1. Gone, gone. One of those is gone, but the 4 is still there. So I'm going to have 1 over 4 secant theta d theta. Yay! And now I have to continue this. Okay, I have to erase it all. All right, so I neatened things up a bit. I bet you didn't even notice. So, poof, everything else is gone. Now I wrote where I got to. So I made that initial trig substitution. I replaced all the x's with thetas, with secants or with tangents, right? So, and then I simplified my radical. I crossed out and I got here. Now I'm going to make it look a little prettier. I have 1/4. Look, just get rid of it to make it easier for yourself. Just take the 1/4. It's a constant. You can move it in the front. That's exactly what I'm going to do. So then I get here. Now, remember, you have to integrate this. I mean, like, people will do this question. They'll do all that crap, and then they'll get there, and then they'll stop. They'll be like, ooh, I got it. It's like, you didn't even integrate. You have to find the antiderivatives. The whole fucking point of doing this. You took something complicated that you cannot possibly integrate. You cannot find an antiderivative of that. It is too complicated. I don't like that my D doesn't meet. I'm going to ruin it. There we go. I didn't ruin it, but I'm such a perfectionist. It's got to look perfect. So I'm going to integrate now. I'm going to replace 1 over secant with our buddy cosine, right? Because cosine is 1 over secant. And, I mean, you can't get any easier to integrate than that. The derivative of sine is cosine. So the antiderivative, when you integrate cosine, you get sine theta plus c. So you did all that crazy. It's like, yeah, I got it. And no, you don't got it, because where are the x's? Right? The original problem had x's in it. Look at it. Does that look like the antiderivative of what you started with? No. I mean, look, in a perfect world, I just want to show you. Like, it should look something like that. Because if I take this derivative, right, I get 1/2. Right? You multiply by the power, subtract 1. This would come on the bottom, right? And don't forget, I mean, there's a 2x there, right? The du. I'd have a 2x. So those 2's would cross out, blah, 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 blah. But this would make the radical come down to the bottom. So I know this final answer has to have something like that in it. There's definitely other stuff with it, but I don't know. So the question is how you do that. And like I said in the lesson video that you probably didn't watch, you're going to solve this. I'm going to write it like this now. I'm going to switch it so that it's secant, right? All I did is just reverse it. Now I'm going to solve for secant. Why are you doing this? Let's see why I'm doing this. I need a triangle. I need to replace the sine of theta. And the only way for me to do that is to create a right triangle, put all three sides there, and then use the trig ratios, right? Opposite hypotenuse, adjacent hypotenuse, right? Your SOHCAHTOA, which I mean, I show this to my students, but I don't use this. I think I say stupid old hobo. Children are happy, or children are hyper. Tangerines are apples, right? I just make up acronyms for them. So, but the problem is I was given secant. I have no idea what the hell secant is. I know what cosine is. So what you do is you take the one you started with, which was secant, solve it for secant, and then replace him with the one you know, which is cosine. Now, I got to flip that over, don't I? Remember, secant is 1 over cosine. So if I'm going to put cosine here, I have to flip that. Now, children are happy. So adjacent hypotenuse. So that means that the adjacent side goes here, right? The adjacent side is always touching the angle. The hypotenuse is always the diagonal. And the opposite side is always the one further away. Now, you're missing that side. You're like, I'm going to use the Pythagorean theorem. No, you're not. You're going to do that if you're a complete moron. I want you to look at the original radical. Whatever was here goes there. You always have all three sides. You don't need to do work for it. Two of the sides are right here in the beginning. This is hypotenuse over adjacent. You're not supposed to know that. You don't know that secant is that. You're supposed to know cosine. So you're given two of the sides right off the bat. The third one is right there. All you have to do is just put that there. You're like, that doesn't work. It does work. If you really want to use the Pythagorean theorem and make sure that's the side, knock yourself out. But I already know that it will be. There has to be. Look at the numbers you have. It x to the 2, right? X squared, b squared, c squared. So with no work, right? You already did a ton of work. You want to do less work. You want to do more work. So you just, whatever that third side is that's not there, you take whatever the original radical was and you put that there. Now, I'm ready. This is not my answer. It's almost my answer. I have to read off the sine of theta. So remember, sine is opposite over hypotenuse. Well, there you go. Opposite hypotenuse, right? That's what sine is. So it's going to be radical x squared minus 4 opposite over the hypotenuse. There you go. Now, if you want, you could make this look pretty. On the top, you get 1 times that. Yeah, make it look pretty. And then I make my minus sign hit my squared. You get that on top. And on the bottom, you can just make it 4x. Right? You have a 1 on top, hooks up with the radical. You have a 4 on the bottom, hooks up with the x. So you can make it look like that. I'd be very happy if you got that far. That, and you know, that is kind of what it should look like. If you were to find the antiderivative of that, you get that. It looks like in the correct form. Like I said, long, complicated problems. You got to pick the correct trig substitution to make. You got to do, take the derivative of it, start plugging them in. You got to simplify the radical part on the side. On the side is very important. On the side, plug everything back in, cross out as much as you can. Now you notice I crossed out a lot of stuff. Everything went away except for a single secant. I used my trig identity to replace that with cosine. I found the integral, my antiderivative, and then I had to draw a right triangle. I didn't have to do any work there. I already had 2 of the sides given to me by what I chose in the very beginning. And then the third side that was missing is in the original question as the radical. And then I just replaced whichever trig dude I had. If I, somehow I had sine here and this was cosine, right? I would have used adjacent hypotenuse. If this somehow had been tangent, I would have did opposite adjacent. Whatever trig dude you land on here, that's what you use the triangle to replace, and then you put the x's back. So I know these problems are very complicated and long, and yes, 3 of them in the test. I have to make sure you can do each type of these replacements. So, all right. So again, I'm going to do just 1 example per video because they're very long and complicated, and I don't want the videos to be, they're already going to be ridiculous. So that was the first example.